Hi ladies and gentlemen. I'm going to work a couple of example problems here for delta epsilons. There aren't any proofs in this course, but you do need to be comfortable with the mechanics and the idea about how we use deltas and epsilons to show limits. Let's start with some definitions and an example. So to start, I want to show the broad picture of what's going on. We don't pick So in general, what we have to do is we have to be given an epsilon value, and the epsilon value is a bound in the output values. The bound is between the function evaluation and the limiting value for the particular input that we're looking at. So we're going to be given that epsilon value first. Once we have that, then we find the associated delta. The delta is a bound on the input. And it's the difference between the input value and the value that we are centered around that is linked up with the limit that we're looking at. So this is the structure that we always use for this type of analysis. We aren't going to do anything in general in this course. Generalizations of this concept are either advanced calculus courses or real analysis courses. What we're doing here is specific examples where we're giving values of epsilon. So remember, the epsilon values are bounding the difference between the function and the limiting value of the function. And then the deltas are the corresponding values between the input of interest, which is A. A is what we're linking up with the limiting value L. So the A input, we're looking around the A input and we're looking at some distance delta away from that input. We're bounded greater than 0 here because we are not going to allow x to actually be equal to A. Because limits are always approaching but never equaling, that's how we can protect by forcing the absolute value to be greater than 0. So let's take a specific look at the type of problem that you're going to have to be comfortable with. So we have our function here, which is a line. I've provided a graph over here because the graphic, I think, makes a big difference when it comes to understanding what's actually going on. Let me write down the verbiage of the problems that you can expect. It'll look something like this. Find delta. So we've been given an epsilon value, or we will be, and we're going to find delta such that the function f of x minus 7, where 7 is the limiting value L, is less than 2. And that is our epsilon value. So they're telling us epsilon is 2, and they want us to find a delta. They're giving us a little bit of additional information. They're telling us the value of A around which we're going to look for input values. So in this case, 0 is less than absolute value of x minus 5, and that's going to be less than some delta. So what we're going to do is we're going to find the delta that is associated with this epsilon. Every epsilon has potentially a different delta and is associated with the value of 5 here. The value of 5 is the input that's corresponding with this limiting value. Those two things are linked to one another. So let's go over here to the graphic so that we can understand, just to help build the intuition as to what's going on. So it's telling us that the value of the limit is here at 7. And then it's telling us that the function value, remember, the function values are on the vertical axis. That's our standard notation. And it tells us that, hey, we're going to bound ourselves so that the difference between the outputs and 7 is always less than 2. So we have, here's plus 2 up here, and then here's minus 2 down here. Now there's a nice tool that is incorporated if you go into the participation and the readings, and it's underneath quantifying closeness. So if you look under quantifying closeness, there's a nice app in there that helps to understand these pictures. All right, so, and let me thicken this up a little bit. So here's our line at 9, and then we have another one down here at 5. And what we want to know is we want to know, hey, what's a delta that keeps the outputs in between these two values? So we need the difference here. That's what this expression is telling us. We need the difference between the f of x and 7 to be somewhere in here. Well, for a line, it's pretty straightforward. The inputs are going to have to be between 4 and 6, and we can see this from the graph. So we see we're centered around 5. That's this 5 right here. So, sorry, it's deleted on me. So the inputs are going to have to be in here. So this is the graphical understanding, just the intuition. We're going to now go through the algebra that gives us this result, because that's what you're going to have to do for the homework problems. But what I want you to understand is they're giving us some range of outputs around the limiting value. And our job is to say, hey, we can make that range of outputs that you require if you keep your inputs inside of this particular range here. That's why we find the delta. Let's take a look at how this goes then. So all we're going to do is we're going to use this information they've given us, f of x minus 7 less than 2. We have the absolute values in there. And we're going to just substitute in the 2x minus 3. So this becomes 2x minus 3 minus 7, and that has to be less than 2. So that's a 2x minus 10 less than 2. And now we're going to remove the absolute values and open this up. And so to remove absolute values, if you don't remember how that works, this is negative 2 has to be less than 2x minus 10, which is less than 2. As long as we're in that range, then we know that we have what we need. What we're looking for, don't lose sight of what we're looking for this x minus 5. So we know we're centered around 5, and we're just looking for kind of the band, if you will, around x minus 5. Well, from this equation, that's pretty straightforward. I can divide the entire inequality here. I call it an equation. It's an inequality, but we can treat it like an equation. Except, of course, when we multiply or divide by a negative number, then we have to swap the direction of the inequalities. So we're going to just divide by 2. We're going to divide everything by 2, and this is going to be minus 1 is less than x minus 5 is less than 1. Well, that notation, reapplying the absolute value, and it just so happens that with a line it's this easy, this is x minus 5 is less than 1. So this has exactly the form that we're looking for right here. We're, of course, bounded away from 0. We have 0, because remember, we're not going to let x equal 5. X minus 5 less than 1. And what this tells us is delta is equal to 1. So for the specific epsilon that the problem gave us, the associated delta value is equal to 1. This is the kind of analysis we want to do. It's algebra. The reason I showed you the graphic over here is to help you understand how the algebra is working to come up with the result. So we bound the output around 7. We're going to let that travel up to plus or minus 2. That's the epsilon value. And then given that epsilon value, we find the associated delta. And we drew in the graphic here, we could see the delta was equal to 1. In general, the graphics don't work. It's just here to help you understand. Let me give you another example. All right, here's another example. We have a function. Again, I've provided a graphic just to help build your intuition. We don't solve these problems using graphics. We actually do the algebra, but I want you to understand what's happening. So what we're going to do this time is we're going to do the algebra, and then we're going to go back and look at the graphic at the very end. So it says let f of x be equal to x plus, or square root of x plus 2, and we want to find a delta such that we are bounded, the output is bounded, the output value, less the limit, which is 3, f of x minus 3, that has to be an absolute value less than 1. So our epsilon value in this case is given, and it's equal to 1. Given that value, we are going to look to bound the input. So we're going to bound x minus 7, and we're going to pick the delta value that makes the statement above here true. That's what we need. So we need this statement right here to be a true statement. And we want to find the delta such that that works. So let's do the algebra first, and then we'll go back and look at the graphic and see how it makes sense. So similar to what we did before, we're going to use absolute value f of x minus 3 less than 1. We're going to substitute in square root of x plus 2 minus 3 less than 1. And then we're going to convert this using the definition of absolute value. This becomes negative 1 is less than the square root of x plus 2 minus 3 less than 1. Now we have this inequality. We could break this up into two separate pieces, or we can work on it together. It doesn't matter which of those things you do. Sometimes it becomes necessary to break it up into the negative 1 portion is less than the function minus 3, and then the function minus 3 is less than 1, and have those be two separate things. For now, I'm going to keep them together. So in this case, I'm going to add 3 to everywhere in the inequality. Adding 3 gives me a 2 is less than square root of x plus 2 is less than 4. And now I'm going to proceed by squaring everywhere through the inequality. And that's going to give me 4 is less than x plus 2 is less than 16. And finally, what I'm going to do is I'm going to subtract off. Well, what do I need to subtract off? I need it to look like x minus 7. So I need to subtract 9 from the inequalities in order to get this piece to be x minus 7. So let me subtract 9 through the entire piece. When I do that, I have minus 5 is less than x plus 2 minus 9 is negative 7. That's what I want. And then that's less than 7. 16 minus 9 is 7. And now I really do have two separate pieces here, right? I have my absolute value of x minus 7 is less than 7. That's if I look at this side over here. Or my absolute value of x minus 7 is less than 5 if I look at this side over here. And the question is, which of these do I want? Is my delta value equal to 5 or is it equal to 7? So it turns out I always pick the smallest number. Delta is going to be the minimum value that I find, and I'll show you why that is in the graphic. But bottom line is, this is my delta value. So my answer to this is delta equals 5. Let's take a look in the graphic why this makes sense. So I'm going to come back up here, and I'm going to look at the fact that I'm expanding around 7. So 7 is here, and I'm going to use the same color scheme. So 7, trying to draw a straight line here at 7. Whoop. And then associated with that is my value of 3. So I'm not quite drawing straight lines here. Apologize for that. Let me do a real quick erasure, and this should come through 7 like this. All right. And now what it tells me is that my output value is less than or equal to 1. So my output value, my difference between my output and 3 right here, has to be less than or equal to 1. So I have this output, and then I have this output way up here. So my output is limited in here. My epsilon, remember, was equal to 1. And so the question is, what is the limit on my input? Well, the input here is 2. This difference is 5. The input over here is way out at 14. And this difference is 7 over here. So what happens if I pick my delta equal to 7? So I have x minus 7 is less than or equal to 7. Well, then I include all the way over here to 0. But if I include 0 in my range of inputs, what does that mean about my output value? Well, the output value is here. for an input at 0. But that output value is outside of my restricted set of outputs. So I can't allow that to happen. That's why I pick the minimum delta value. I pick the 5 because if I restrict the 5 up here, that's no problem. The output value, when I put in a 12, I'm going to have square root of 14. But the point is, this output value here is still inside of my requirement. It still is inside of this inequality right here, which is what I have to have. So I can't pick the 7, or else I get an output value which is outside of my restricted range. So I have to pick the smaller delta value. That's how these delta epsilons work when you give me a specific epsilon. Then I go through and I do the algebra to find the delta. If I come up with multiple values, which I generally will, not always, but I generally will when I have a function that is not a straight line, then I pick the smaller of the values because that's going to restrict the outputs. By restricting the inputs, by picking the smaller value, I will restrict the outputs. Thanks very much.